How many electrons does chlorine have? So let's review. Chlorine's right there. It has how many electrons? 17 electrons, right? Okay, so let's put 17 electrons in. Well, let's count the number of electrons.
If I were to have 17 electrons, how many is that? Where would I put them? So first, the first two in the first shell. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Notice that I will only go up to the third shell to answer this question. Okay, so
how do I write that? Well, remember I said I have the first 2 is in the first shell, so I say 2. Then I filled up that shell, so I moved to the second shell where I have 8, right? So I filled up that shell with 8. And finally, I filled up the third shell with 7 more to give me a total of 17. So that's called 2, 8, 7. Great. Now let's do that again with silicon. Silicon has what? 14 electrons. So we need to somehow fill up 14 electrons. So let's say 2 plus 8 is 10. How many more do we need to get to 14? Just 4. Great. Aluminum is 13. Right? So 13 would be 2. 8 is already 10. Plus how many more to get 13? 3. Yep. Boron is 5. So how do we go to 5? 2 plus, is it 8? No, because 2 plus 8 is 10, right? So you can't go beyond that. So you say 3 only. 2, 3. Potassium is 19. So I'm going to say 2, 8 is 10. How many more in the third row? Maximum is 8. Good. So that's 2, 8, 8. That is 18. But this is 19. So how many do we need? 1. Very good. All right. Magnesium is 12. So 12 is 2 plus 8 is 10 plus 2 is 12. Great. So again, the total number of electrons is 17. Let's fill out this column first. Aluminum, again, was 13. Potassium is 19. Magnesium is 12. Carbon is 6. Hydrogen is 1. Oxygen is 8. Okay, so to figure out what is the number of valence electrons. So one way to figure out the number of valence electrons is using the electron level arrangement that we just did here. So for example, valence electron is basically the outermost electrons. So it's asking you how many electrons exist in the outermost shell. So for example, chlorine, the outermost shell has 7 electrons. Okay? Aluminum, there's 3 electrons. Potassium, there's 1 electron. Silicon, no, we didn't do silicon. We did magnesium, there's 2 electrons. Okay, so did you notice any patterns there? Right, so let's take a look at the periodic table. Chlorine is in what group? It's in group 7A, right? Okay. What about magnesium? Magnesium is in group 2A, right? Aluminum is in group 3A. Potassium is in group 1A, right? And then how many valence electron does potassium have? 1. How many does magnesium have? 2. How many does aluminum have? 3. How many does chlorine have? 7. Right? So you notice the pattern there? So it turns out the number of valence electrons depend on the column these elements are in. So if 1A, you have 1 electron, 2A, you have two 2 electrons, valence electrons. And if you're in 3A, you have 3 valence electrons. If you're in 7A, you have 7 valence electrons. So if we were to ask how many valence electrons does oxygen have, what would you say? Well, what group is it in? It's in 6A, so it has 6 valence electrons. Yeah, so that's a quick and easy way of doing that instead of writing the whole electron configuration and seeing what the last number is. That's a shortcut. So we just figured out that oxygen has 6 valence electron. How many does carbon have? It's in group 4A, right? So it has 4 valence electrons. How about hydrogen? It's in group 1A, so it has 1 valence electrons. Very good. And that concept is going to be very important in the next chapter, so it's good to have practice now. All right, finally, we're going to use, we already seen that the periodic table has a lot of trends that we can see just based on the valence electron right there that we just looked at. But now the rest of the chapter will talk about other trends found in the periodic table. So the first one is talking about the size of an atom, all right? Now, remember from the lecture, I'm just going to explain in one direction first. If you go from left to right on the periodic table, what's happening? Well, if you go from left to right on the periodic table, you're increasing in atoms. Let me say that one more time. When you go from the left to the right on the periodic table, you are increasing in number of protons you have, correct? And the proton number is also equal to the number of electrons. So, for example, if you are a hydrogen, right, you have only 1 electron and 1 proton. Whereas your helium, you have 2 electrons and 2 protons. Remember, the size of an atom is basically the proton measured out to the electrons, correct? So if you have only 1 proton and 1 electron versus something that with two protons and 2 electrons, that attraction is greater than this helium attraction is greater than the attraction found in hydrogen, right? Because there's 2 versus only 1 pairs. Because if there's a greater attraction between the electrons versus the protons, when things are attracted to each other, what do? They come closer together, right? Right? So the electrons are coming closer to the center of the atoms. Well, if it comes closer, it's getting smaller. Yeah? Okay, so that explains the trend as you go from left to right, that the atoms do get smaller. What about the trend going downward? Again, remember that the size of an atom is between the nucleus, the distance between the nucleus and the outermost electrons. When you go down the periodic table, each time you jump a row, what are you also increasing by? You are increasing by another shell, right? So you have, remember those 8 electrons? If you're jumping another shell, you're getting bigger or larger, the distance. It's getting larger. So as you go down the periodic table, the size is getting bigger. Okay, so knowing those 2 trends will help us solve these problems. Taking a look at the first problem here, oxygen versus sulfur. Oxygen is here. Oxygen is here. Sulfur is below it. So which one's bigger? The one below, right? Very good. So sulfur is larger. Second one, silicon. Silicon, where is silicon? Silicon's here. And chlorine is here. Okay, so chlorine's more to the right, so it's going to be smaller. So silicon is going to be larger. Lastly, iron, Fe, is here, and fluorine is here. Okay, well, iron is not only lower than fluorine is, but also more to the left, so iron is going to be the larger one. Great. Okay, next trend is ionization energy. And ionization energy is basically the energy required to remove the valence electron. Okay, so let's imagine this. If you are a electron that's close to the nucleus versus an electron that's very far away from the nucleus, which one is it easier to remove? Right? It's easier to remove the one that's farther away because it has it's less controlled by this nucleus. So to answer this question, just take a look at the size of the atom. The larger the atom is, the lower, so larger atom, the lower the ionization energy. The smaller the atom, the higher the ionization energy. So it's actually the opposite trend, right? So from left to right, you are going to increase in IE. From top to bottom, you are going to decrease in ionization energy. Okay, so let's take a look. Nitrogen, this is becoming a mess. It's okay. We will live with it. Okay, so nitrogen and carbon. Where's nitrogen? Nitrogen's right here. Where's carbon? Carbon's right here. So that means nitrogen is smaller than carbon. If nitrogen is smaller than carbon, then it's going to have a greater ionization energy. You're looking for the smaller atom. Versus sodium and potassium. Sodium is here. Potassium is here. So which one is smaller? Sodium is smaller. Lastly, chlorine is here. And sodium is here. Which one's smaller? Chlorine is smaller, right? Because it's more to the right. Excellent. Okay, now lastly, metallic character. It turns out metals are elements that love to give away electrons, right? Loves give electrons away. Okay, so if it loves to give electrons away, it must have a small ionization energy. Okay, so it has a small ionization energy, then as you go from left to right, this character would do what? Would it increase or would it decrease? Remember that it increases in ionization as you go from left to right. So you're going to decrease in metal character as you go from left to right. On the left-hand side, you have elements that has low ionization energy, therefore very metallic-like. Whereas on the right-hand side, you have elements that have high ionization energy. High ionization energy means not very metal-like. Okay? So that's left to right. How about from top to bottom? From top to bottom. As you go down the periodic table, you are decreasing in ionization energy, so therefore you are going to be increasing in metal character. So what do you notice? This is an increase as you go down, much like it's an increase in size as you go down. As you go from left to right, you are decreasing in metal character, just like when you go left to right, you are decreasing in atom size. So those two patterns are exactly the same as each other. So we're basically looking for the bigger atom in this case. Yeah. Copper, let's use a different color. Copper is here versus carbon. Carbon is here. Which one's more metallic? Copper is more low and more to the left, so copper is more metallic. How about Fe, iron, and cobalt, Co? Where is Co? Co is right next to it. Which one's more metallic? Iron is more to the left, so iron is more metallic. Palladium and zinc. Palladium is lower and also to the left, so palladium is more metallic. All right, cool.